A W, a Z, Boson, and a top Quark walk into a bar. Yeah, it's beginning to a terrible joke. Oh, what's this? Wait a second. That friend looks a little familiar. Well, you all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one rule ad. I don't think it rules them all. And it might be just hyper-ruleal turtles all the way down.
Yes, it's on the back of an infinite number of hyper-ruleal turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Name's here. Yes, late as usual. Do I have anything useful to share? Probably not. If we happen to exist in a realm where maybe this might be a wee bit interesting, well, maybe you'll want to stick around. But here we go. So while I was on the Wolfram Alphas and everything, looking a little bit into the Higgs boson, make some random claims. It's like, I don't know if it's true. Again, we need more significant digits. Those are very valuable. A lot of human beings have spent literally millions of human years figuring that stuff out. Thank you. So where are we going right now? All right. As we teased over here, what are we looking at? Okay. So again, the links to the main condensed forms are in the doobly-doo and everything. Some of it's basic algebra that I'm literally still learning and everything. But okay, what do we have here? We have our Higgs particle. Okay, and we're going to get into some of the deep lore or just a very elementary Big Think article highlighting a study that apparently refuted the 7 sigma deviance claim of something that happened in 2022 for one of the other ones. Again, we make mistakes. We try to do better. Okay, so what do we have here? We have the Higgs particle. We have its mass. So I literally, Higgs boson, mass. And then I compared it to the listed mass of the Z boson. What's the Z boson? Z boson, it conveniently has it all right here for us. It's 91.19 giga electron volts. Divided by the speed of light there, we pop out a mass term. Why? Because that's how science works. They do the calculations and it ends up making sense because it seems to work. All right. Where are we now? Hey, Jax. Thank you for joining, my friend. Good to see you. But, okay. So long story short, I looked, basically making the assumption that there's some closed form. Why? Because I'm pretty sure if it was just like 4 pi or 2 pi to get to that, people probably would have already put in the thing. What would that mean? I don't know. Maybe a circular rotation, kind of like Planck's constant. And we divide out that 2 pi to get h bar. Why? It's an elementary unit of action. And then when you do the full cycle, we do that for some other things, which is very interesting. But essentially, unless you've kind of paid attention to some of the stuff that Thad's been working with a model of the minimal arena, I like to call it the HF8 model, personally, because one of the core geometric objects is the hyperbolic figure 8 knots complement. Yes, real deep lore. But essentially, it's made up of a double cover, the Giesking manifold, which is basically the Giesking constant that we see here. Okay, happens to also be the volume complement of the minimal 3 manifold, at least according to Wikipedia and the other stuff that you can actually look up. But, oh, and it has the square root of 2 built into that, which I thought was neat. I'm like, square root of 2? I seem to see that a lot in quantum mechanics, or 1 over the square root of 2. Why? Because it's irrational. What does that mean? Apparently, it's extremely useful for probabilities and stuff like that. There may be other reasons, but I'm not metaphysical enough to get into that. But okay, so it gives us this result. What is this? Okay, so if it's all right, was it 80? Wait, no, this one 91.19. That seems to be pretty close. Maybe it's a hair off, but I believe when as if you at least put it in. Oh, excuse me. the other forms. This is what's important. It took me a while. I had to go back to the poster to figure out how Thad did those magical expansions with the nested radicals and everything. Why? Because I'm pretty sure I could turn that 2 into something. What did we turn it into with other notation? This. So you can turn that same division into the equivalent form of the square root of 32 over the figure 8 knots hyperbolic volume. So that's basically 2 Giesking manifolds for their volume constants, and to the 4th power. Why 32? Okay. At least, again, within the model, the minimal arena you're talking about, the Planck temperature has 32 derangements, or 32. There's something there. What is there? We don't know. But basically, 32 is related to the temperature zone. And anytime you can get the figure 8 knot, the Giesking constant or anything there, that tends to work pretty well, or at least so far. And again, I'm not saying this is an actual thing. This is just an interesting thing. And again, feel free to play around. Like I say, this is a solution to anything, but not to be fair, I limited it as stuff. My level of confidence, again, we need more significant digits, and to be fair, there should actually be a second part too. Okay, so that's, I mean, if we have 4 digits there, 4 significant digits, that seems to fit pretty well. And just to drive it home, at least according to Wolfram Alpha, and again, it only has so many significant digits, it at least shows the result as what? Oh, because you can actually multiply it if you move the 32 to the denominator. That's what I was trying to show. I know. Extremely long-winded as always. Okay. And then while making a mistake, I got this. Okay. Basically, I divided when I was trying to multiply, or I swapped the numerator and the denominator. And I got this result. And I'm like, what does this result mean? And I'm like, okay, it's too high for that. That's pretty large, though. It's about 172 giga-electron volts. Okay. So I can also rewrite that. Again, just multiplying it. Just swap numerator and denominator gives me this. Okay. So I did a wee bit of investigation. I'm looking up, like, is there anything we know of that has something within the realm of 172 giga-electron volts? Well, let me to the top quark. I was interested. So I go into here, and I'm like, okay. Apparently has, then again, just mass. We're not saying anything else about the charge and stuff like that. Has a mass of 172.76 giga-electron volts. Okay. And we got some errors there, and I'm like, okay. So the error, okay, so it could be 173 or a little over 100 and, what is it, 172.4 or 6-ish. Okay. So there's some error there. Okay, so that's kind of in the range. So let's see if we can get a little closer. So we have that. We divide. Okay, 1%. What's 1%? A lot. Now I'm like, all right. So let me multiply it by something. Well, the Giesking constant, because we already used it. It's actually in there. Just 2 by that. I just use VFE for notation purposes. I guess it's a little too high. What if I take its square root? That seems to be right about 173. I think it's 173.06 or something like that-ish. That seems to be within the range of the error bars that we had over there. What was that? Oh, laundry's done. All right. 100. Oh, yeah, about 173. Okay, again. Try just a happy coincidence. Now, you should comment that on the video, because otherwise I'm not going to remember, Jax. I apologize. Okay. So we pop over here. I'm like, okay, so let's move on, blah, blah, blah. Okay. So how about the W boson mass? Okay. To be fair, I think I actually made a mistake and looked for a map from the Z boson. Why do I say this? Because this is what I came up with. Still the Higgs boson mass. We have our VFE to the 4th, so square root all that, and then I was over 32 within the root. And then I found this. It was like, oh, it was like 22 imaginary infinite tower powers of I divided by 9. So I'm like, wait a second. If I multiplied that by 2, that would be, oh, look, 44 over 18. Well, the claim is there's 44 things going on with the time boundary for the Planck time magnitude of 44 or negative 44. And then, oh, the charge boundary. The Planck charge is a magnitude of 18 because it's negative 18 coulombs. Well, that's really cool. And then it gives us this. So it says that there. So you're like, all right, what is that? It says it's the W plus and minus because depending on the charge. So you can just do the sign convention. You add a minus sign in there. Why? Because maths. Actual interpretation, hey, that's fine. But it leads you to that number. I'm like, okay. Can we have confidence in that number at all? Because what is it? Gives us about 80 GeV squared. Okay. So let's go into it a little bit deeper. Why? Because it's interesting. Okay. Because apparently I heard something back, I think it was like 2022. It was a W boson deviation. Oh, it's a little bit out there. It's like, oh, apparently it exceeded a particular mass threshold that, to summarize, if it's above, I think it's about 170. No, if it's like 80.4 gigaelectron volts for the W boson, a little bit above that, apparently then that seems to imply that, well, supersymmetry is probably a thing. We could look for all these other particles. If it falls a little below that, it's starting to gain more credence that maybe supersymmetry, as we currently have it conceit, maybe isn't the best answer. And again, links in the doobly-doo. Feel free to read it for yourself. So what was it? In 2022, Fermilab CDF collaboration released a shocking claim that the W boson mass was much higher than previously thought, which challenged everything. With no results from the LHC, the picture finally clears up. Okay, so they go over the constraints, blah, blah, blah. Basically had about a 7 sigma deviation. Blah, blah, blah. Okay. So initial evidence indicated that top Quark's mass in terms of energy equivalent could be anywhere between about 165 GeV to up to 180 GeV. Okay, it's about 173 as we just saw, which would constrain the W boson to be no lower than 80.33 GeV for a low mass top quark. I don't know what that means for a low mass top. Oh, yeah, big energy scales and because amplitudes and everything, and no greater than 80.40 GeV for a high mass top quark. Okay. So we go through here. That basically the CDF 2022 measurement was 80.433 GeV with an uncertainty of basically 0.0094. Okay. That's what they attached to it. You could have that measurement if you had a high error bar, but that's according to what they got. So basically, they went through, and ultimately it appears that... okay, so here's the pictures. So this was the outlier here, or it's a claim outlier because it has small error bars. As you can see, there's some more outliers, but they have much larger error bars. And then you have other ones with some fairly small error bars that seem to be within the standard model prediction. Okay, so as of right now, oh, okay, maybe the top mass is actually a little smaller. Maybe I should have adjusted it, divided by a square root of d-ski. Okay. Okay, so basically right now they're at, where's the final one? It's after that little loopy diagram. Oh, so ill prepared. How much is, okay. So now they're at basically world average of the W boson. 80.3 80.369 plus or minus 0.013 GeV. All right, so 80.369, 80.379. Okay. Okay, so appears to be within the error bars there. And again, take it for what it's worth. That's a complex thing. There should be two parts there. There's just some fun numerology. If there's something there, that would be pretty cool. If anything, I would have more confidence in the Z boson just because if you had something as simple as this, that's pretty simple. And then if you expand it out, you could find something. And again, I'm very biased here. I'm very biased. I'm a proponent of the model of the minimal arena. Why? It seems to make sense. I was invited. And it seems to be actually making predictions. And a dude like me on the internet can actually try to figure things out. That and at least doing all these calculations all the time. I can actually start to listen to different people presenting presentations, be like, I'll refer to the technical paper. And then actually like quickly do some calculation, kind of see what they're talking about and be like, oh, okay, they missed a 2 pi here or something. Or maybe it's on the paper, maybe they just forgot in the PowerPoint. Because nobody's ever forgotten anything. For anything. Ever. Yeah. But that's all I got. Just figured I'd put that out there for anybody that's interested. But other than that, take care of yourselves, everybody. It's a wacky and wild world out there. But I'm betting on humanity. Why? Because we can. Peace out, everybody.